Here's some objects sitting on a chair in my office. I wanted to take a picture and show you some things. And of course, now there's so many things around us and so many pictures we can take that it's overwhelming. This picture was shot with the Samsung Galaxy S23 Plus. Samsung has a Pro mode that allows us to shoot both RAW format and JPEG. Here's the image of the RAW format on the left and the processed JPEG on the right. The Samsung sensor is actually 100 megapixels. The RAW format is only 12 megapixels, so there isn't really such a thing as RAW anymore. It's already been processed in some form. We see on the right is that the Samsung processing, even though it's JPEG, has greatly improved the image. If we keep zooming in, we see artifacts in the JPEG image. Here you see we've zoomed in a bit more, and you see that it's pixelated, not quite as smooth as the RAW image. Obviously, the pixel blocks are not real, so let's get rid of them. Here we upsampled the image in the center using the multi-scale deep super resolution network, and on the right by the enhanced deep super resolution network. Both of these were developed by Seoul National University. The point of showing you these images is just as we zoom in to emphasize that it never makes sense to show the raw pixels. We can always do better, so let's talk about how. Computational imaging. Episode 13, Wiener filtering. So in episode 12, we talked about the 5 main algorithms that have been developed for estimation of images from measured data. The first being isomorphism, just report the image as the measurements. And then we talked about linear regression and constrained optimization. So all three methods that generalize on the regression theme, and then the next two methods will use Bayesian algorithms. In the case of the first one, where we're going to report the measurement or the object just as being equal to the measurement, this is the common idea of photography. So in photography, we have a remote object F, and we take a picture that looks like the remote object, but the object is blurred by the point spread function or the impulse response as shown here. And we want to think about, is just reporting G is equal to F or F is equal to G our best bet? Can't we do better? And we're going to do this in the context of Wiener filtering. So we have this Jupyter Notebook on the GitHub repository, on the Computational Imaging GitHub repository, that explores estimation of F when there's a simple convolution as the measurement. And we use as a database for evaluating this the Chianti database of astrophysical data. One of the central challenges of image science is finding databases of representative images to evaluate algorithms, and we'll use several throughout the course, but throughout image science there's a central problem of developing the right data. In a one-dimensional case, this is a very useful database, is this Chianti database of astrophysical data. Unfortunately, we're not using it here for any of its intended purpose. We're just using it as a database of one-dimensional signals we can use to evaluate algorithms. If we dig into the Chianti database, you can find the spectral lines of all sorts of representative atomic species. In this case, this is a particular ion of iron, and we've looked at it over the range of 200 to 300 angstroms, and we see a number of sharp spectral lines. As you zoom in, you would find even more spectral lines, but at this resolution, these are the main ones that come out. Now, this is evaluated at a particular temperature and density. If we ask the database to give us the spectral lines at an elevated temperature and an elevated density, the lines will blur, as you see at the lower right. So now in this case, this is the true object. The lines are blurred by the internal physics of the object. And we see that there's these features that, for example, this doublet at 220 angstroms and some features around 230 angstroms that are quite interesting. So we'd like to measure those, but we need to measure them with an instrument that has a finite pixel response. So something is going to happen in the spectral measurement that's going to blur the system. In the simulation that we've implemented in this notebook, we're going to assume that the detector just measures the spectrum, but with a rectangular pixel, so that there's a integration with the boxcar, the rect function. We're going to convolve the function with the rect function. And what you see is that the measured spectrum, which is shown in red here, has now blurred. And so you might look at this and say, well, this doublet at 220 angstroms and this interesting feature at 225 or 230 angstroms can no longer be resolved. So you just say, well, that's life. That's the measured spectrum. But you could say, can't we do better? Couldn't we do something to try to recover the signal? So to start with that, we need a forward model. And so we have the forward model that the signal f of x has been convolved with the system impulse response, which in this case would be the rect function, and then some noise has been added to the system in this measurement process. Okay, so that's it. That's our forward model. Now the central problem of this chapter is how do we estimate f given g? So one thing we could do is say, well, this is a convolution. We know that if we take the Fourier transform, we can turn this into an algebraic form, so that the Fourier transform of the measurements, g hat of u, is equal to the Fourier transform of the unknown signal times the transfer function, the Fourier transform of the impulse response, plus the noise spectrum. Well, that seems easy enough. So then you say, okay, well, this is now algebraic. I'll just divide by the transfer function and I'll recover the signals. And now we have this f hat of u is equal to the estimated signal. And now we have this pesky term over here, which is the noise divided by the transfer function. That could all be very fine if the transfer function has a large magnitude. But any place where the transfer function has a very small magnitude, if there's, for example, a zero of the transfer function, that would create a very large noise term. It would amplify the noise and really drown out the signal. So one could say, well, this doesn't seem like it necessarily would be a good idea. There would be a lot of noise in the reconstruction. Is there some optimal filter we could use, this w hat of u, that would produce a better result than just dividing by the transfer function? So Norbert Wiener considered this question back in the 1940s and wanted to choose a filter that would minimize the error. So now we're considering the regression error for this system as a function of frequency. And so we have the estimated spectrum minus the true spectrum, magnitude squared, and then these brackets mean expectation values. So we're going to take the expectation value of the difference in the spectral terms. If we assume that we're going to use this optimal filter, W, we can say that F estimate is H times F, or W times H times F. And so if we, here we're just assuming that F estimate is equal to this WH, and so we get the WH squared, and then we have these cross terms. Now we're going to take the expectation of F squared and assume that that is our power spectrum for the signal, so that we have a mean power spectrum for the signal, and we have a mean noise power spectrum, which would be the expectation of magnitude of the noise squared, and so our error turns into this term under that assumption. So now we can differentiate this with respect to W and find the value of W of U that minimizes the error. And that turns out to have this form. It's equal to the conjugate of the transfer function times the power spectral density of the signal divided by the magnitude of the transfer function squared times the signal plus the noise. So here, if H somehow went to 0, then W would go to 0. So we're not going to estimate the signal for frequencies where the transfer function is equal to 0. If H is large, so that the noise is smaller than the signal, then this would basically turn into the 1 over h. So at points where h is large, the filter is equal to 1 over the transfer function, and places where h is small, the filter goes to 0. The air noise, then we can evaluate what is the expected noise, and it turns out to be equal to this. If h is large and the signal is large, then the noise is going to be equal to the noise variance divided by the transfer function. So it would just be the variance would be equal to the noise. If, on the other hand, h goes to 0, then the error is equal to the signal power spectrum density. We have points in the spectrum where there's no measurement, where h is 0, our error is complete. The noise is equal to the signal, but the noise hasn't exploded. We don't get the alternative that we had earlier was that the noise goes to infinity at points where h is equal to 0, which is very, very important. So we just say we're going to damp those out and not measure the signal at points where h is equal to 0. So we can go apply this to the spectral signals that we looked at before. Here we're assuming different SNR levels. So basically, if we take the Wiener filter and divide through by the noise, we could represent the signal power spectrum density S sub f divided by the noise as our signal to noise ratio, and so we're assuming that we have a noisy measurement. We've added noise to the measurement, and we have the red again is the measured spectrum, and you see the doublets blurred out. But if we apply the Wiener filter, the doublet reappears, and we're able to resolve features that we might not otherwise see. The doublet becomes much clearer and much cleaner down here, where the signal to noise ratio is 1000. So the lines become very sharp. But we also see that the Wiener filter introduces these artifacts, and this is due to the fact that h in this case is a rectangular function, so the h has side lobes, and the Wiener filter in this case introduces side lobes as well. The Jupyter Notebook includes measurements where we've apodized the measurement function so that we could use like a smoother spline, and then we could you could actually reduce the side lobes by apodizing the measurement function. But this is our basic strategy for, and showing a simple strategy for estimation of the signal deconvolution here, where we were not willing to accept the blurred signal, and we try to recover and improve the signal even in the presence of this blur. Now, as we saw at the beginning of today's lecture, more recently people use neural methods that will do much better than the Wiener filter, but the Wiener filter is a good introduction to the idea that one can improve signal estimation, and historically extremely important. It can be, of course, applied in 2 dimensions. The Wiener filter is built into the scikit image library in Python. It has the restoration with the Wiener filter. We can assume that we have our blurred image here, snake D, and we have a PSF that we know, and then the regularization number in this filter is 1 over the signal to noise ratio. And here's an example where the image has been blurred by a Gaussian PSF, and then is recovered by the Wiener filter using this algorithm. So that's an introduction to the first and simplest algorithm, where we're just going to take isomorphic data and try to deconvolve and sharpen it. Next time we'll consider this same problem, but in the context of a shift variance system, and we come up with a very similar solution. Earlier we looked at singular value decomposition of shift variant forward models. We found that those systems were described by singular values, lambda sub I here, and that if the singular value is small, very similar to what we saw with the Wiener filter, noise is amplified if we try to estimate signal components for small singular values. And so we'll introduce Tikhonov regularization by adding a term similar to the term added in the Wiener filter to dampen the impact of small singular values. But we'll save that for the next lecture.